Okay, so one of the things I'm doing, I took a moment to do just now, was actually start live streaming. So that'll record this lecture and that'll be available. I can post it later, just kind of to have a backup plan in case somebody's sick and can't come to class. It'll be there. We'll cover all my expectations about attendance in a couple minutes, but so first of all, I want to say hello, give you just a little bit about myself, and then ask you a few questions about yourselves. We're going to have a little kind of, not a quiz, but a pre-class survey kind of thing, partly getting to know you, partly just seeing where you're at with a couple of kind of units problems. That'll sort of guide the rest of today and Tuesday. So what I'd like for you to do is get some sort of a device that's connected to the internet and go to kahoot.it. We're going to do a Kahoot quiz sort of thing. Later in the semester, if I do these for credit, today we're just kind of doing it for fun, so you can put your name or whatever. But in the future, we'll use your 89 number here, so I can take it into Excel. So you go to kahoot.it, punch in that game pin, and then put in a I'll use this as a way to tell you a little bit about myself as you tell me about yourselves. Should be everybody and somebody extra that I don't recognize. Okay, gotcha. Gotcha. Okay, cool. All right. Okay, so with that, let's get started. So, what genre of environmental engineering are you most interested in? Would it be natural and environmental, so sort of the natural environment and remediation, global environmental challenges and policy, water quality and treatment, or air quality? Okay, so a lot of remediation, water quality and treatment. All right, cool. So just a little bit about my background. I went to school at Georgia Tech in Atlanta, and because my family lived nearby Atlanta, so it was kind of the natural pick for me. So I did my undergraduate in Earth and Atmospheric Science, did a fair bit about air quality, but my focus was sort of water chemistry, geochemistry. I kind of grew up loving to play in the creek behind my house and go fishing and all that, and I had aquariums. So I always liked water, and so kind of my interest in natural systems pertaining to water was pretty apparent. So my undergraduate was actually not engineering, it was Earth and Atmospheric Science. I took some engineering classes, and they make you take a lot of engineering related classes there anyway, so it worked out for me to switch into environmental engineering as a graduate student, and I stayed there to switch programs and really studied disinfection processes primarily in graduate school. So that's kind of my the essence of my academic background. And then I worked for about half a year at a position in Michigan. I moved to Michigan for a couple of years, and I was working as a wastewater permitter. So we'll talk about that towards the end of the course, but it's National Pollutant Discharge Elimination system, basically a way to treat our wastewater. It's like, how do we regulate our wastewater discharges? So I have a little bit of wastewater background, but a lot of drinking water and related technologies part of the background. Don't worry about these scores. This is just, I had to mark some correct answer. So none of those were incorrect or whatever. Okay, so how long have you been interested in studying environmental engineering? Kind of gave you my answer there. Okay, so more recent. So tell me about it. Anybody have any stories or reasons you chose it? Did it just look fun, interesting?
I started off wanting to do agricultural engineering because I grew up in a farming town.
Mm-hmm.
I was like, that's too limited, and I found out what environmental was.
Cool. Okay.
I started off over here in mechanical engineering, and I actually switched to civil engineering.
Okay.
This is a required class for that. I'm taking more of an interest in the general infrastructure.
Okay, so are you technically a civil major then?
Yes.
So I think you should be in my noon class instead of this one. Today, it's no problem today. We just have segmented them off differently, so we do more chemistry in this version. So you'll probably be happier in the other one. Do you have courses at noon right now?
No.
Okay, so don't bother going today, but you'll want to switch into that one that's offered at noon. It's a slightly bigger class. That one happens to be in PFT, but we do less chemistry. So you'll if you don't, unless you love chemistry, you should be a little happier with that. But it's no problem. No problem at all. Anybody else? Any other civil majors that? Yeah, it's sort of silly why we do it. It isn't strictly necessary, but for accreditation and stuff, we've decided to split them. All right. Okay. So next up, how old are you? And I'm going to give you a range, so you don't have to give an exact. I turned 35 this summer. Okay, so all of you are just right in that junior second. Actually, when I do that question for my civil course, they have a little more freedom of when they take it. So it's sometimes they'll get and people from other disciplines as well. So sometimes I'll get a bigger range. All right. Where are you from? And to simplify that, I'm just going to ask where you spent most of your childhood. I mentioned for myself as suburbs of Atlanta, so north, about half hour north of Atlanta. Okay. All right. So almost all of you from Louisiana, and then somebody a state or two away. And technically, I'm 3 states away from Georgia. All right. So, considering our different course categories, which are you least comfortable with? Would it be unit conversions, word problems in general, mass balances, chemistry, or biological processes? Okay, kind of a range. Does that mean some of you feel great about everything? It's like, whatever. All of you are just like, Anything specifically scary or intimidating about these? Anything you feel like, oh, you've seen that before, but never clicked? Okay, so I'm going to put a picture here, and what does that make you think of? Chemistry quiz of sorts. You got a full minute on this one. Okay. So it looks like a lot of you, no one got the joke. Okay, so a lot of you rightly recognize Fe as iron, and there was an oxygen in there, so you think of iron oxide. A couple of you thinking you're real smart, and you're like, hey, that's not realistic chemical structure. You're exactly right. I'm just gonna say that maybe our one civil student hates chemistry. I'll just no need to answer. I'm just I always tease my civil engineers for that, so we'll leave it there, even if that's not true. But none of you got the joke. So it's a Ferris wheel, because iron is ferric or ferrous in the different oxidation states. And so if you put it like this, those are all, ferrous versions of iron. And so it's a Ferris wheel, like what you see in the state fair. So puns. And actually that's the reason I remember I never have to think about it too hard, what the difference between is ferrous 2+ or is ferric, it's 2+ and 3+, which one's which. My sister got me a shirt with something like that on it a while back, and it's Fe2+. And I was like, okay, Ferris wheel. Fe2+ is ferrous. Okay. So, and on that note, do you enjoy a good pun? Okay, we have at least one person cringing. Pretty muted reactions, though, so it must just be a dreary morning. Hardly a laugh. Maybe you all hate puns. Okay, whiteboards are remarkable. Time flies like an arrow. Fruit flies like a banana. Well, nobody finds the punishing. Okay, well that's maybe you do like them. It's just morning. Okay, fine. Okay, we're gonna not do that one just yet. If I can, I'm sure I can pause it. So I'm gonna come back to this. Actually, I'm not sure if I have a way to pause. Let's see what happens. We can skip forward to that later. But I wanted to kind of go through a bit of lecture and come back to that example that we mentioned. Before we do that, I'll talk a little bit about the course. We'll go through the syllabus. I'll have all of that posted to Moodle by Wednesday or Thursday. Actually, that's what I'm aiming for, before next class. But it'll depend a little bit on when I get added to be able to manage the Moodles. I think I have access to this one, so maybe I'll do that sooner anyway. So I want to take a look through the syllabus with you. So bring that over. All right. That's not very helpful. Okay, so you know just a little bit about me now. Got my office info there. I do work from home sometimes, so occasionally it might just be easier to meet over Zoom. That's totally possible. I plan to be in my office essentially after this class on Thursdays, probably be on Tuesdays as well, but I'm going to try to protect my Thursdays, particularly for office hours at 11 a.m. to noon. Of course, you can always email me and ask for another time to meet. Happy to meet. Okay, the textbook. I have a copy of it here. I do encourage you all to get it. It's a great help for a lot of different topics. It's a nice level that's approachable, kind of wherever you are. It'll go into a little bit of depth, but not so much that it loses you in terms of like what's going on with why you care about it. In my opinion, So I would encourage you to get it. It's got a lot of fundamentals that are helpful for environmental science and engineering. There are several other supplemental recommended resources here. Most of these are available online, so that's just more info if you want to go there. You can get them on the LSU library. Occasionally, I'm going to be pulling some material from these as well. So even though I say this is our textbook, technically it only has a chapter or two directly related to water and wastewater treatment. And so I'm going to supplement that for membranes, for example, from other texts. And I'll try to post those sections for you as we go to Moodle. Okay, objectives are pretty standard. We want to learn about water and wastewater treatment. We want to be able to perform calculations for unit design, different operations, as you might expect. Grading, I changed it a bit this year from years past. So, and I know you guys largely won't care about what I did in the past in a sense, but I'm telling you that because I know that I'm making an adjustment, and so I don't want to take all the experience I've had teaching this course in the past and apply it to you guys when I've changed something. So I'm going to tell you about what I used to do and why I changed it, and hopefully you can give me feedback if as needed along the way for that. So what I changed, well, first of all, the scheme is here, 400 points total, exam 1, 2, and 3. That would be 3/4 of the grade total. And then we have homework and participation making up the remaining 100 combined. So what I changed is I used to have more weight on homework and more weight on participation. And the reason I'm changing this is because I realized that as more and more of my homework assignments and graded solutions were out there, whether it be Chegg or whatever, there'd be a lot of students, unfortunately, would just find those materials and copy paste or work from those. And my intent for the homework and for the grading is homework is practice and gives you a chance to see how much you learn, how much you know, how much you don't know, and prepare for the exams in that manner. And I wanted to reward people based on how much they're learning. And what eventually was happening is I was rewarding people for not learning, grade-wise, and penalizing people who were learning and therefore occasionally making mistakes on the homeworks. So given that, I recognize stuff's out there. I'm just going to be grading the homeworks for completion, and it's up to you to make it useful and learn from it. So I'm not awarding quite as many points for that at this time around, and likewise, since that participation in the homework is kind of participation in the course, I've also I've adjusted it so essentially that combination of whatever in-class stuff we do for the class participation could be we'll look at it in a moment, but that could be quizzes, kind of like what we were doing today, or it could be could just be attendance. How often do I see you here? If you were absent, but you messaged me and said, "Hey, I'm gonna tune in online," and then you say hello online and stuff. That would, I know that you're actively participating, and I want to award you credit grade-wise based on how much you've learned. And one way I think you learn is just by being here. Sometimes I'll just say random stuff. It's interesting. You're learning something even if it doesn't get tested, right? So I want to award you for that. My theory is grades should reflect how much you learn more than anything else. So I aim for that, even if it's not always ideal. Okay, homeworks. Kind of talked about them already. I'm going to have you submit them in Moodle. I'm basically going to just check them for if you made the attempt and showed me a clear answer. That's what I look for. So do make the habit of outlining your answer, show your work, all of that. If you're going to request extra time, you need to talk to me or something like that. That would be I'm not offering that. That's just general expectations. If if you were going to miss a deadline for something that you thought was reasonable and out of your control, do let me know. Exams are pretty standard. We'll be in class. Essentially, we'll have exam 1 will cover the first third of the course. Exam 2, and we'll take a look at that in a minute in terms of what that will be, what topics. Exam 2 will be the second third, and then the final exam will be that last portion will be kind of our wastewater biological treatment kind of stuff, and then it will incorporate a little bit of the first 2 sections. So it's a little bit comprehensive, and you'll find that the course in general is kind of comprehensive in that we go from mass balances and expand those into different systems, and we kind of see that theme all the way through as mass balance, unit conversions, all of that, thinking about how to design, what kind of equations do we need to create to design a system. Okay, I talked about class participation and attendance. You've already participated a bit in Moodle, Kahoot. Occasionally I might use Moodle quizzes for something, but I'll probably just stick to Kahoot in class. If I do a Moodle thing, it'll probably be like I assign a reading and ask you to take this quiz on the reading on your own time or something. So I'll email you if I'm going to do something like that. Okay. Of course, academic dishonesty will not be tolerated. And for our tentative schedule here, of course, today we're saying hello. We don't have Moodle up yet, but that'll be there next time. We'll touch the mass balance and chemistry a little bit today, and then really finish that review for tomorrow, or excuse me, on Thursday, kind of a rehash on basic mass balance, make sure everybody's on the same page, go through some of the chemistry. From there, we'll go to drinking water treatment processes. And by the way, the civil structure for this course that I teach for the civil students is very similar. I just spend a little more time on chemistry background here at the start of the course. Membrane filtration for us will be before our first exam. So the first exam will be essentially these physical processes, treatment processes, which will include sedimentation, coagulation, flocculation. That does incorporate some chemistry there, granular filtration, and membrane filtration. I think where the civil side, membrane filtration will probably be after the first exam. From there, we get into more chemical-based treatment. So it's sort of segmented to physical mostly, chemical mostly, and then biological mostly. That's sort of the overall structure. So we'll go into disinfection, quantification, what kind of tools, chlorination, advanced oxidation processes, and then water softening. So ultraviolet light is maybe photochemistry a bit. Could also think of it a little bit as just physics. But overall, that's generally chemistry-driven topics. We'll probably have a seminar on the Flint water crisis. I was in Michigan for 2 years and overlapped with that there, so I learned a lot about it. My wife at the time was working in public health and worked tangentially on some of the issues there. So we have a lot to say. I think is interesting and worthwhile for you. And then we'll get into wastewater treatment. So a lot of the activated sludge, different processes involved with that. So after the exam 1, we'll have the fall break, October 13th, and Thanksgiving after the second exam. Final exam time posted here is current as of a couple days ago when I checked. Sometimes LSU has to change that, so when it gets closer to time, we definitely should double check, make sure I didn't get that wrong or it didn't change or anything like that. But tentatively, that would be Thursday, December 8th. Okay, any questions, issues, comments? One of the things I meant to mention regarding attendance, I do expect you to be here and participating in class. As I mentioned, I think that's one marker of you're going to learn something if you happen to be present. And so generally that's my expectation. I do have this set up so that if you scroll to the top, you can find the lecture live. In fact, maybe I'll show you real quick. It's going to be a little bit of not deja vu, but a little bit inception here. So you can see what's happening as I try to viewing myself, and all that. So that's going on right now, and I'm just going to stop the headache before we get too far there. So essentially, if there is a case where you let me know you have to miss, that's going to be available. And then my plan is to post those recordings. Maybe sometimes I will just leave the lecture itself there. It'll stay on that Twitch page for I think it's 10 days. So if I don't transfer it to YouTube, then it'll be gone. But I'm planning to do that. So just be warned if I'm doing like a homework review, I'll definitely post it for you. But if it's like today's lecture, if I forget and it's been 10 days, then it'll be gone. So just keep that in mind. But I think you could download it on your own if you really wanted to from there. So that's viewable on that page, and then I'll link it in the middle. Okay, so, but that's not to excuse you for not being here, right? So I want you to be here. If you're sick and have a fever and still want to participate in class, this is a way to do it, right? Without coming here and sharing. Sharing is not caring for sickness, right? All right. With that, I'm going to come back to our PowerPoint. All right, so just like I said, going to do just a little bit of kind of a high-level picture of what water treatment is about and how it fits into environmental engineering more generally. And really, honestly, most of environmental engineering you can think of as some sort of process where you're taking some stuff that is in some media, so some stuff in some other stuff, some particles in the air, some bacteria in the water, some stuff in some stuff, right? So you've got, let's say, some water with a bunch of particles and stuff in it. Then you send it through some sort of process, and that's what we're aiming to design. We want to transform or remove or separate or somehow manipulate those things so that we get cleaner water. Maybe there's a couple pieces here left, but then we have one little pile of stuff that we can throw into the landfill, for example. Maybe rather than do that process, maybe we are inactivating them, and so they're some sort of organism. We prevent them from replicating. We don't even have to kill them so long as they can't reproduce. Then it's disinfected. Those bacteria can no longer infect something if they can't multiply. It's totally fine to have, let's say, an Ebola virus injected into your blood, so long as it's been deactivated so that it can't replicate and it can't cause replication, right? And hopefully no way to repair so that it could. So that's kind of the big picture is we want to transfer or transform mass. I say mass, sometimes we'll talk about number instead of mass. In the case of viruses or bacteria, it's hard to weigh them. It's much easier to count them, and so we often do so. So it'll be conservation of mass or really matter is the essence of what we're going to talk about. Okay, so as a quick overview for our class here, for the water treatment side, really what we are dealing with is treatment based on certain health standards that the EPA and that are essentially our governing bodies have decided we should maintain these health standards in particular because we want to have healthy populations, right? So we want to make sure that it's not going to cause any health harms. That's where we have the health standards. We also have some aesthetic standards. Those are not required. So health is a mandatory consideration, whereas the aesthetic are optional. So if your water is coming out of your tap and it's yellow, maybe that's okay. Maybe it meets all the health standards. It might just have some yellow food coloring in it. And it's perfectly safe to drink. But that's not aesthetically pleasing. And so typically people would object, right? So the common users would object to that. And so then we'd have some issue. So those are kind of the two guiding principles for our water treatment. We'll talk more about them later. For our wastewater treatment, really what we want to do is protect intended uses of whatever body of water we're going to be discharging waste into. Because really in wastewater, what we're talking about is we want to treat it such that it's not going to pollute our lakes and rivers to the point where you can no longer enjoy them. So you can see a kind of a low resolution picture here. This is wastewater effluent flowing through a landfill in Nicaragua. It's a pretty terrible situation. And you can see it's like neon green practically. That's actually algae that grew in the wastewater lagoon. Certainly, it's not likely to have received adequate treatment. Even the fact that you see all the algae kind of suggests that as well. So kind of a worst case scenario there. We don't want that. We also don't want our rivers to catch on fire. This has happened in our history just a few decades ago. We'll show some examples of that when we get to wastewater. We want to be able to go fishing in our waters, to have wildlife, to do boating, swimming, all of this. We want to protect our water supplies. And in general, many people really like to have flourishing ecology around, to explore, to understand, to have access to nature in a pristine or as close to it as we can condition. So all of those things are good things, positive things for humanity that we want. Of course, having the ability to discharge wastewater is also a positive thing for humanity. So that's our challenge, right? Is to be able to treat in such a manner that it's not going to cost us all the wealth in the world to get it as pure as we possibly can and then discharge it into kind of a muddy lake. That doesn't actually make sense. In fact, in a way, we could harm an ecosystem if you think about it, discharging absolutely, completely pure, just water into a system that, let's say it's a brackish water system. Well, you're changing the salinity. So there's interesting things to think about that. Okay, so we talked about the syllabus and the book for those of you who came in a little late. This is our book. I'm encouraging you to get it. It's a great resource for environmental science and engineering, kind of the principles. You could probably get by if you have a study partner and just one of you has it, but I've kept my original copy from when I used this some time ago when I was in school and have since started teaching with it. So I've tried teaching from some other textbooks and I have not liked them very much in comparison. So I do recommend it. I like the level that it of instruction it gives. I think it's pretty approachable. Talked about the syllabus already, but so quick little recap. It's not on Moodle yet because I haven't built the Moodle pages yet. Had some access issues, so that'll be coming soon, hopefully before next class. The essence here is we have 2 midterms, 1 final. Probably can expect about 4 homework assignments, possibly 5. These will be kind of chemistry and units, sedimentation, coagulation, filtration, then disinfection, advanced oxidation, water softening, and then wrapping up with the biological treatment. We'll have some participation in class quizzes sometimes. And in fact, I did, oops. It's funny. I have little controls on my writing pad that I didn't know about. Sorry. I forgot to mention this when we were talking about the participation, but one of the changes I made with homeworks, so that now that I'm just counting them as for completion, I may add a quiz on the day homeworks are due to have in class to give you a little bit of a challenge and to challenge you to be correct with that type of a problem, right? So that it's a sort of an add-on to the homework. Okay, now that you've done the homework, can you apply this to an in-class test as a prequel to the test? So that's one of the things I will try to do for you, and that will go into the participation part of the grade. And just real quick for those who arrived late, each exam will be weighted the same 100 points, and then we have homeworks at 50 points total and class participation at 50. And my aim there is to grade based on how much you learn. Okay, I'm going to go ahead and give you a reading assignment. When I do make the Moodle in the next day or two, I'll post this on there. This is an interesting read. It's a cryptosporidium outbreak. This is a major public health crisis that was caused by improper water treatment. This is cryptosporidium is a parasite. It's, if you think about the different types of microorganisms, we've got viruses, which are basically just complicated little proteins with some protection. Then you have bacteria, which are single-cell organisms that are very small and have just a membrane protecting them, not like a full cell wall that's got like rigid structure. And then we have what you might call parasites, so in the class like amoeba, we have these eukaryotic single-cell organisms, cryptosporidium being one of them, and they can form these little cysts that are protected and can survive treatment processes better than a bacteria. And so what happened was, you can read this, it's the scientific article. It's actually quite a good read. You don't feel like you have to understand and get into every technical aspect, but read enough to see what it's talking about and what are the key points, right? Essentially, they accidentally concentrated lots and lots of these cryptosporidium spores, and ultimately they were released into the Milwaukee water distribution system, and many thousands of people became sick. And cryptosporidiosis, on the one hand, it gives you diarrhea for several months, which is unpleasant and almost could be humorous in a gross sort of way, except that it also is very dangerous for immunocompromised people. So there's actually a lot of deaths that were associated with it. And so this was quite an issue, and we really didn't know a whole lot about cryptosporidium before that. So I think it probably helped the world to understand a little more about what this disease is. Okay, so I'm going to post that. I think it's a kind of a neat encapsulation of a lot of our course. Okay, so we'll just spend a few more minutes and kind of, again, do that high-level overview of what kind of skills we need here. Units are essential, so whatever problem we're doing, paying attention to the units is going to be probably your number one best tool to understand what's happening with the system. Because we're always going to be conserving mass, so we're never going to have a system where the mass magically disappears or materializes. There's always going to be some source or sink or transformation that's described and that we're working with. So even if you forget how specifically to solve a problem, taking the units and following them and making sure you keep your units consistent is going to give you a pretty good chance at getting to the right answer, even if you forgot kind of where you are with a problem. Mass balances are what we're going to do essentially with these units and do in the course generally. Essentially what we're saying is if we have some amount of mass coming into a system, then, and I don't think it'll work very well with this scale actually, essentially how much we have coming in is going to relate to how much is going out if we have the same amount within the system at all times. So if we have, let's say, 5 units of stuff coming inside the system, we could have 100 units going in here so long as we have an equal number of units leaving. And we just happen to have what we call a steady state of 5 inside that box at all times. We just have a lot going through it. Does that make sense? We could also just change this and say, okay, we have 10 going in and 10 going out different directions. Same thing. That's a very quick and dirty description of what is a steady state system. We have a steady amount of the stuff inside it, even though stuff is coming in, stuff is going out. And stuff could be going out by a reaction, let's say, that just destroys it. Whereas some of it's going out just the tailpipe, right? Some of it's physically moving out, some of it's being destroyed. And so as we think about mass balances, that's kind of the concept here, right? Is how are we changing it? We could have a growth. We could have growth of bacteria, but as long as we're keeping the same amount inside a steady state, then we could say, okay, we have 5 coming in, 5 growing, and 10 leaving. It would stay at steady state. So that's kind of a small microcosm of mass balances, and we can add to them and work with them, but that's going to give us a way to understand how to design these processes. Because a lot of times that reaction that's happening inside is going to depend on how much is there. So we have to have good control of how much is in there. And if we can manage a system at steady state, it makes it a lot easier because we then know, oh, it's always this amount. We don't have to change our math from second to second based on the changing situation because we've designed the system to keep a steady state operation. Chemistry is actually mostly units, especially for any of you who are less comfortable with chemistry. This may be a great help because essentially everything we do, even the molar conversions, it's really just about, okay, how many of these are going to react? It's units. And we can, once we look at it and from a frame of mind that it's all about the units, I think that will help with that. We'll deal with chemical equilibria. These are going to be important for several operations, so that's going to be something that if you're not familiar with, we will refamiliarize you with. There's some SI conversions that I expect everybody to be familiar with and have kind of ready on the top of your head. And again, I apologize for the projector screen being not quite right. But this is, we'll just go, first of all, I expect everybody to be familiar with, SI scales generally, that this exists. But specifically, I would hope that at least in this range, you're pretty familiar. Maybe you haven't used mega very often, that's 1 million, but kilo definitely, like a kilogram, kilometer, kilometer. Obviously, we don't use hecto or deca very often, but you should be aware that that's, it goes in that order. We do use deci sometimes, decimal, deciliter. Pretty rare to see it, but it's there. Centi, of course, should know. It's like centurion, right? That cent. That's 1 in 1,000, or excuse me, 1 in 100. Millis, 1 in 1,000. Micro, we're going to use a fair bit, 1 in 1,000,000. So if you haven't seen that before, and then nano, maybe we won't use a whole lot, but you should be familiar with that in the environmental field because that's 1 in 1 billion, and that's going to be, we'll actually see that fairly frequently with nanograms, nanoparticles, different things. It'll come up. maybe not in our class, but keep that in mind. And essentially what I'm telling you is I expect you to have this on hand so that you have micrograms per liter given to you on an exam. You're not freaking out. You've remembered to take a look over this. So if that's not something that's in your mind already, make a point to study that a little bit. Okay, so then we have just a note on the exams. I'm going to give you a small formula list and this table here for essentially this is temperature versus several different things. So you can see on the left off screen there is just units of 0, 5, 10, 15, 20, and so on degrees Celsius. And essentially one thing I want to call your attention to, because we'll use this one pretty frequently. Okay, we have density, dynamic viscosity. Again, on the theme of paying attention to units, if we take a look at this unit here, it contains a multiplier within the unit itself. So when we go and look up, let's say 5 degrees Celsius, and we're looking at the density there and the dynamic viscosity, this dynamic viscosity is not just 1.518, it's 1.518 and add the unit, and add the whole unit, right? So that's 1.518 times 10 to the minus third kilograms per meter per second. So that times 10 to the minus third is what I'm calling your attention to, because I know a lot of people will miss that. So units, right? And you could even see the same thing as, not that we're going to use this ever, but same thing happens in the next one and several others. So just reiterating the units thing. Okay, a few things to know. You should be able to convert between liters and cubic meters. This is very handy. I don't expect that everyone already knew this, but there are 1,000 liters in 1 cubic meter. So this is a 1 liter bottle. So we take 1,000 of these to fill a 1 meter cubed, which would probably be something like that, maybe that tall. So 1,000 of them. And if you think about it physically, you put a couple of our desks here together, or just, take a look at the wall here with these. You could even do that in class on an exam, right? Just be thinking about these blocks of cement. Okay, well, the water bottle is like there. How many of those are you going to need to fill in a meter cubed, right? And if your answer is looking like, a trillion, you probably did something wrong. Or if it's like 10, you probably did something wrong. So use a little bit of, if you can, it'll be good to start relating real life things to these dimensions and conversions. That'll help you out a lot. Another one would be, there's 1 milliliter and 1 centimeter. This might look a little funny because we just talked about milli versus centi, but this is due to the way volumes convert. So, and this is a good reminder here. So if we take 1 meter and we cube it, and we compare that to, well, first of all, let me do this. Let's say we say 1 meter is equal to 100 centimeters, right? That's kind of the definition. But if we want to do cubed, in order to cube it, we actually have to put the cube outside of parentheses like this. We cannot just say, oh, that 1 meter cubed is equal to 100 cubic centimeters. No, that is not correct. And again, if you visualize this, if you think about it, a centimeter is less than an inch. So let's just imagine an inch, right? It's going to be less than this. And you take this 1 cubic inch that you can fit between your fingers, and you make 100 of those. Is that going to fill this thing? No, definitely not. And so you have to think about it, or that, again, it would be a good way to check it. You have to put these parentheses here so that you're cubing the conversion factor as well as the unit, right? Which will make sense when you realize, oh, you've got 100 centimeters this way, and then you've got 100 centimeters this way, and then 100 centimeters out, that's going to be your conversion. So it's 100 cubed. So 1 cubic meter is equal to 100 cubic centimeters. Okay. So just a quick little reminder there, and that's why when we convert to 1 milliliter, which is 1,000th of a liter, that's not 1 millimeter cubed. Okay, so one thing we could do is take a look at, and this would be a challenge for you guys, answer how many grams are in 1 milliliter of water at 5 degrees Celsius. So a moment ago, we looked at the density of water, kilograms per cubic meter, so exactly 1,000 at 5 degrees Celsius. So I'm going to say the density of water at 5 degrees Celsius is 1,000 kilograms per cubic meter. So given that, see if you can answer that question. How many grams are in 1 milliliter of water? I'll give you a few minutes to work on that. All right, so a few ways you could probably approach this. What I'm going to do here, because it's making sense to me at the moment, is to say, well, we just talked about that there's 1,000 liters in 1 cubic meter. So we can say this is going to be 1,000 kilograms. Instead of per 1 cubic meter, I'm going to say per 1,000 liters. If you wanted to be elaborate about that, of course, you could say, okay, 1,000 kilograms per cubic meter times 1 cubic meter per 1,000 liters. That would be a more explicit way to do it. You could cancel your units, and that'll get you your 1,000 kilograms per 1,000 liters. And that also means that that's 1 kilogram per liter at that temperature. Actually, this is how we define, in a sense, what is a kilogram is the mass of 1 liter of water at 5 degrees Celsius. So it's actually a very key unit here. Okay, so with that, we can say, all right, well, we have 1 kilogram and 1 liter. So then in a milliliter is the question. So we could take 1 kilogram per 1 liter, multiply that, and say, okay, well, for every 1 liter, we have 1,000 milliliters. And so then we get 0.001 kilogram per milliliter. And then we need to convert from kilograms to grams. And you probably already see this here, but we have, for every 1,000 grams, we have 1 kilogram. And so that'll lead us to 1.0 grams per milliliter. Okay, so pretty straightforward at the end of the day, but it kind of makes you think, kind of causes you to be like, okay, well, what am I doing with this density? So hopefully that's helpful, just kind of getting your mind on the units, how we're going to have to use them sometimes, and so on. Apologize, I'm off the edge again. I'll spend a few minutes with this projector once we stop and try to get that up. See if I can fix that. Okay, so that's just unit conversion generally. There's a few specific types that are going to be really important for chemistry. It's numbers to mass. And I have a little fun analogy for you. So if we're thinking about the molar units, that's probably, if you think back to high school chemistry or whatever, if you were frustrated with chemistry, this is probably why, because it just didn't maybe quite make sense. So consider that when you want to know how a reaction is going to go, it often depends on how many rather than the mass of the molecules. So the number is oftentimes more important than the weight of them. So if you think about like the word dozen is the same type of a function as a mole. So a mole is 6.02 times 10 to the 23rd molecules per mole. A dozen is 12 of something, right? It's 12 eggs per dozen or whatever. And so then if you think about how that works, I'm going to skip. I think I might skip ahead in a moment. You might realize that if you were to use eggs for something, whether it's for cooking or for maybe doing something very naughty and egging somebody's car, you wouldn't probably wouldn't make a weight comparison. You know, it's like, okay, I want 2 pounds of bread loaves. I'm probably don't even use eggs in most breads, but anyway, you probably aren't going to say, okay, well then I need a proportional weight of eggs, right? Maybe there's some proportionality, but certainly it kind of changes if you're going to egg somebody's car. You know, you don't need 1 ton of eggs for 1 car. You just need a dozen or something, right? You select how much you want, and how much of a nuisance and a felon you want to be, not a felon, but whatever. And you select that number of eggs. It's a ratio based on the number, right? If you needed to egg 5 cars, maybe that's 5 half dozens or something. I don't know. So that's kind of the point, and this was the where I wanted to go to with the eggs there. Okay, so I think I'm going to leave it off there. We'll pick up here and then kind of finish out a bit of a chemistry overview next time. Before we go, any questions? Any thoughts for the course? Okay, so we'll pick up here. We'll do a little bit of chemistry review next time, and see you on Thursday.